Now we are going to proceed with our next presenter and the next presentation. Caroline Piffet, apologies for my pronunciation, it's not very well, is working at CELABOR since 2022. CELABOR is a research center based in Belgium, involved in the circular economy and bioeconomy. She is a chemist, of course, having done a PhD thesis in inorganic chemistry at the University of Liège in Belgium. After working for 1 year in the plastic industry in the R&D section before joining CELABOR in the material department, bio-based materials, paper, board, packaging, textile, and so on. She has worked on several research projects and on specific analysis for customers. In the ESTELLA sister project, they are developing cellulose nanofibers as bio-based and biodegradable additive to reinforce the mechanical properties of the recycled resin systems developed by partners. Her presentation is about scientific modification of cellulose nanofibers to improve their dispersion in epoxy resins. Caroline, the floor is yours. Thank you.
Thank you for the kind introduction. I will share my screen. Do you hear me properly first?
Yes.
Yes.
Yeah, I can hear you well. Yeah, everything looks great. Thank you.
Okay, perfect. So thank you first for the organization of this nice seminar and the opportunity to present and share you some results of the ESTELLA project, and more particularly results from a CELABOR partner from this project. So I will talk to you about today the specific modification of cellulose nanofibers to improve the dispersion in epoxy resins. So I will first introduce you a bit about CELABOR and the ESTELLA project and some concepts. Then I will explain our strategy for the modification of the cellulose and the effects of the cellulose on the composite properties, and finally a short conclusion. So first about CELABOR, we are a Belgian private scientific and technical center based in the Walloon region in Belgium. And so we offer scientific and technical support to companies implied in the circular economy and bioeconomy with different sectors, including agro-food, green processes, packaging, textile, and environment. We are about 50 people, mainly scientific profiles, and we are making different kinds of activities such as testing and analysis with a lot of tests under accreditations, expertise, and of course R&D with national and international collaboration with different financial teams. And so our society is divided in 4 departments. First, food technologies, then environment, which is more for waste and water analysis. The material department where I work, we are mainly active on packaging, plastic, papers, cardboard, and textile and bio-based materials. And the extraction department, who is active in the extraction of biomass compounds for different application and valorization. We don't work separately. We have a lot of interaction between the departments to valorize the biomass in the different application and sector. The ESTELLA project now. So the acronym is design of bio-based thermoset polymer with recycling capability by dynamic bonds for biocomposite manufacturing. We are 13 partners in 8 countries The project started in June 2022 for 42 months with the Horizon Europe Innovation Program. The coordinator is CIDO Lab in Spain. And here is our internet site if you're interested to have more information. And, oh, the slide doesn't go next. Yes, here. And so a bit of context about the project. So the goal is to have circular loops for the newer thermoset design. So starting from the raw materials up to the reuse and recyclability with high value application. So currently the thermoset, as we know, are unrecyclable compounds and generated a high volume of waste. And we would like to design new composite materials, but with a high recyclability rate to decrease our environmental impact. And of course, this new composite should keep excellent properties for a wide range of application. Here in the ESTELLA project, the composite we designed are oriented for two main applications, which are the windows frame and the platform for a scooter. We also develop recyclable, so these resins are recyclable and should be integrated in current techniques. So we want to be sure that the manufacturer and recycler don't have to modify the sites to include the new resin. This should be includable in the current flow of waste. At CELABOR, we are mainly involved in the early stage of the fabrication of those new resins. We developed specific cellulose nanofibers as bio-based and biodegradable reinforcement additive with high compatibility with the developed resins. And why should we work on a reinforcement additive is because the new resins have the risk to be less performant as the mechanical properties. And so to compensate and to avoid this, we use a reinforcement additive. So the strategy for the current thermoset, as I said, are no recyclable, so they are simply grinded to obtain a powder mixture, and those polymers are mainly made about amide links. In the new recyclable and biodegradable resins, we have different strategies that can be followed. And in the ESTELLA project, we have different possibilities also that are studied. So first, for the recycling mechanism, we developed some resins that can be simply destroyed by reversible links between the precursors. And so the reversible thermoset composite can be remolded, or we can collect the monomers and the reinforcement fibers separately, depending on the precursors that are used. The other option is to degrade the new resin that are studied. And we study in the ESTELLA project the biological degradation by microorganisms with different mechanisms, which are the fully degradable degradation of the composite. In that case, you don't recycle the resin or the fibers. You have the no waste at the end. The other option is to attack the fibers and collect the monomers, and so to obtain the new precursors that can be reused again. And the third possibility is to degrade the resin and keep the fibers, and those fibers can be reused in new thermosets. And in order to develop those kind of resin, we concentrated our research efforts on reversible bonds like ester or Diels alder, and on degradable resins also. So now I will switch to the result of the project. And so first, at CELABOR, we produced the cellulose nanofibers. So I will explain you how we proceed. So we have our cellulose, which is a polymer that can react chemically. And we performed an oxidation with tempo reactant. This oxidation allowed us to graft a carboxylate group on the polymer chains. So we obtained this kind of compound. And then when we have this pre-treated cellulose, we proceeded to a mechanical treatment, the defibrillation, in order to have nanofibers. So the cellulose is composed of fibrils, which are composed of microfiber, which are composed of nanofibers. And with the mechanical treatment, we will destroy and separate the nanofibers one from the others to obtain separate fibers, as we saw in the previous presentation. And the technique we used for the mechanical treatment is the high pressure homogenization. So this is this kind of machine, and the cellulose is put in water. Then this mixture go in a holes which is very, very thin, and because of shearing, this causes the separation of the nanofibers. This technique was chosen into the ESTELLA project because it is upscalable, and we would like to have also more industriable production as possible. And thanks to this technique, we obtained the cellulose nanofibers functionalized with the carboxylate groups. This is, as we already see, a jelly aqueous dispersion, low concentration, about 1%. Then, when we have our nanocellulose fibers in water, we have to face to a challenge, because now we have to include this solution into the epoxy resins, but we have an aqueous media, and the resins precursor are not compatible with the water to avoid degradation. So if we start by the simplest way, we dried by freeze drying or another technique, but we used freeze drying the cellulose. We obtained a dried product of cellulose functionalized, and this can be included in the precursor of the resins. But the problem is that when you dried the cellulose nanofibers, it is very, very difficult to disperse again those nanofibers, because the hydrogen bonds between the cellulose chains are very high, and you obtain only pieces of nanofibers not properly dispersed, even at very low concentration. So we decided to develop a new strategy, and this strategy consists in pre-blend the aqueous nanofibers with the resin precursor at a high concentration. and then redisperse this master batch into the resin precursor to achieve the target concentration. So first we prepared an emulsion between the aqueous dispersion of nanofibers and the resin precursor. This is homogeneously mixed with limited time of the resin precursor in contact with water to avoid degradation. We dry this emulsion to obtain the nanofibers dispersed at a ratio of 50% into the precursor. We call this the master batch, and this master batch is dispersed into the resin precursor at the concentration we wanted to have it at the end. And then we can add the hardener and to proceed to the curing of the resin. And at the end, the goal is to obtain a resin with 1 to 5% of nanofibers. So we started our development with commercial resins, and the first challenge we have to face is the high viscosity of the media. So you can see here what the emulsion looks like. Then after the freeze drying, we have the master batch looking like this. And when we disperse this into the precursor, so the precursor is the same that is already included into the master batch, of course, we achieve to disperse around 1.5%, but this is not the concentration that we will have into the resin because you still have to add the hardener. So it is not a lot of fibers. And you see that when we try to increase just a little bit up to 2%, it is already too much. The media is very viscous even when we eat. And we have still some master batch pieces not very properly dispersed. So we decided to vary the functionalization rate of the cellulose nanofibers to see if this strategy could help us to increase the dispersion of the nanofibers. So we have, as a reminder, this functionalization with carboxylate groups grafted on the cellulose, and we varied the tempo reactant ratio by decreasing from the ratio we used at the beginning. We call this 1:1, and we decreased up to 16 times this ratio. And you can see in the IR spectroscopy that we have the carboxylate groups decreasing. And the dosage by ICP spectroscopy confirmed this qualitative observation. So with ICP spectroscopy, we saturated the carboxylate group with sodium ion, and we dosed the sodium ion, and by calculation, we obtained the corresponding functionalization ratio. And you can see that we well decreased when we decrease the tempo reactant concentration. So starting from 20% and going up to 2%. On this functionalization had, of course, some consequence on the viscosity. And so you can see that when we decrease the tempo ratio, we have lower viscosity. So this is the viscosity of the cellulose at nanofibers at 1% in water. And this is because the higher the viscosity, the thinner the fibers. We have also an effect on the transparency of the samples. So you can see that with high ratio of functionalization, we have a high transparency of the samples, and with low functionalization ratio, we have a low transparency. And this is because the higher the transparency, the shorter the fiber. Then still on the characterization of those different cellulose, you can see also that what we just saw in the viscosity and UV spectroscopy is confirmed by the observation with optical microscopy. You can see that with high ratio of functionalization, we don't see the fibers into the optical microscopy, but these are bigger and longer and thicker with low functionalization ratio. And then still on the commercial resins, we try to see the maximum ratio of nanofibers that can be included in that system. And you can see that for the very thin nanofibers, we could go up to 1.2% of nanofibers. And for the longer, we could go up to 6%. So this is, of course, the ratio for one kind of resin. It will depend on the viscosity and the ratio on the precursors and the hardeners. But this shows that by tuning the functionalization ratio, we can tune also the ratio of additive that can be included in those resins. For the next steps of the project, we selected two types of functionalization because we cannot work on everything. And so we choose to work on this one, the thinner and shorter fiber, and on the 1/8 to have sufficiently carboxylated content. Those resins were reproduced to have confirmation of the result, of course, but also to have sufficient samples for characterization of the mechanical properties. And we performed compression tests, and so saw the compression modulus with different ratio of nanofibers, the 1,1 and the 1/8 that were selected. And so you can see here the reference resin have a compression modulus at 1,850. And the compression modulus is significantly increased when adding 0.1% of cellulose nanofibers 1,1 and 1% of cellulose nanofibers 1/8. You can see also that it seems that if we increase too much the cellulose ratio, the compression modulus decrease, probably because some aggregates are present and can make fragilization points into the samples. We also looked at different ratio precursor hardeners. So the commercial resin we used is recommended by the supplier 100 to 35, and we tried different ratio with addition of 1% of cellulose nanofibers 1/8, and you can see that whatever the ratio, the blue samples here is with the addition of nanofibers, and we can see an effect of the addition of the nanofibers on the compression modulus. Then we transposed the strategy up to the ESTELLA Project resins. So the resin developed by our partner from Komaijski Institute in Slovenia are modified lignin recyclable resins. So we decided to look to prepare, with the same strategy. So preparing an emulsion, a master batch, dispersing this master batch, and adding the hardener. Here we have an additional challenge, is that for those resin, we have to use THF as a solvent during the preparation of the resins, but the nanofibers precipitate in THF, so there is an additional incompatibility between the different components. So we have here the reference resin, how it looks like. And even with this additional challenge, we managed to add 1% of cellulose tempo nanofibers, so the one, the very thin. And you can see here, it's not very regular, but it's not very important. It was because of the mold. It's not on the quality of the samples. And when we measure the Shore D of this sample, so to quantify the hardness, you can see a very significant increase of the Shore D, which is about twice when we add 1% of those nanofibers. Then the second case of transposition of our developed method is with the Diels-Alder reversible resins from Wageningen partner, and we had to adapt our specific chemical grafting. So first, we started with the same functionalization with carboxylate group, and then we proceeded to a second chemical treatment to graft furfuramine groups on the cellulose. With the ICP spectroscopy and the IR spectroscopy, we confirmed that we have nearly 100% of the cellulose of the tempo oxidation that is transformed after that in furfuramine on the cellulose chains, so very high grafting ratio. Then with the same mechanical treatment, we produced the cellulose grafted with furfuramine, and it is the same as for the other grafted cellulose nanofibers, 1% dispersion in water because it is still very jelly and viscous. Then with the similar strategy as for the other, we prepared the emulsion with the precursor we received from our partners, dried to form the master batch, and then dispersed the master batch into the resin precursor. And then we send it back to Wageningen so that they can cure the resin and make different tests with different reactant and curing ratio, and also to see the impact on the nanofibers on the curing for this specific Diels-Alder, because here the specific point is that the cellulose nanofibers are grafted with the reactive group directly. And so to conclude, for this ESTELLA and CELABOR results, we achieved to functionalize the cellulose with different functional groups, carboxylate and furfuramine. We developed an efficient method to disperse the cellulose nanofibers into commercial resin, and we transposed this methodology to the recyclable resins of the project, and we showed the impact of the cellulose nanofibers on the mechanical properties, on the Shore D and compression modulus. So this is what I wanted to share with you. Thank you for your attention, and feel free to ask if you have any question.